For decades, we assumed Apollo 12 was finished. The crew came home in 1969, the hardware was accounted for. One piece was not. In September 2002, an amateur astronomer found a faint object moving against the stars. Everyone assumed it was an asteroid until the orbit solution came back. It was not passing the Earth, it was going around it. Which means something had come back to us after more than 30 years away. Something we had built, launched, and written off within hours of it leaving the pad. And if the identification is right, then this object spent 31 years going around the Sun before finding its way home, and to this day, we still cannot prove exactly where it had been. So, let's follow it back. The discovery itself was almost boring. September 3rd, 2002. An amateur astronomer named Bill Young is pointing an 18-inch telescope at a patch of empty sky and letting a camera stare at it for 10 seconds at a time. He is looking for asteroids. Most nights, nothing happens. Then, the software finds something. A faint smear of light moving against the fixed stars. Young does what any careful observer does. He measures its position, records the time, and sends the numbers to the people whose job it is to work out what a moving dot actually is. The object is given a temporary designation, J002E3. That is not a name. It is a filing code, the sort of label handed out to a few hundred new asteroid candidates every month. And for a few days, that is exactly what everyone assumes it is, a rock drifting past on its way to somewhere else. Then the orbit solution comes back. Now, to understand why that caused a problem, you have to understand what is supposed to be up there. The Earth has one large natural satellite, the Moon. That is the entire list. Everything else in orbit around our planet is either a spacecraft we put there, a piece of a spacecraft we put there, or a fragment of something that used to be a spacecraft we put there. And all of that hardware sits relatively close to home. Beyond a certain distance, the situation changes. Out where the Moon's gravity and the Sun's gravity start pulling with real force, nothing stays put. An object that far out gets tugged from 3 directions at once, and over time, those tugs add up. The orbit stretches, wobbles, and eventually breaks. The object either falls inward, hits something, or gets flung out of the system entirely. So, a large object sitting in a distant orbit around the Earth is not just unusual, it is a contradiction. It should not be able to stay there long enough for us to find it. Which meant one of 2 things had to be true. Either this object had arrived very recently, or our understanding of the region was wrong. The first explanation was easy to test. If something had recently entered Earth orbit, it almost certainly came from a rocket launch. Every launch is catalogued. Every discarded upper stage is tracked, at least for a while. So astronomers checked the launch records against the orbit. Nothing matched. There was no recent mission that could have left this object where it was. And that is where a routine sky survey turned into something else entirely. Before going any further, it is worth being clear about what is actually being claimed here, because the claim is larger than it first appears. It is this. In November 1969, a piece of hardware was supposed to leave the Earth-Moon system permanently. It failed to leave. It spent roughly 2 years going around the Earth in an orbit that should not have held it. In 1971, it finally escaped and went into orbit around the Sun. It stayed there for 31 years. In 2002, it came back, looped the Earth about 6 times over the course of a year, and in June 2003, it left again. That is the journey. Written out, it takes 10 seconds to say. Now here is the part that makes it difficult. Nobody watched any of it. There was no transmitter on this object. Nothing was listening for it. It carried no beacon, no power source, and no instrument of any kind. From the moment it was written off in 1969, there was no reason for a single telescope anywhere on Earth to point at it, and as far as the records show, none did. So there are no photographs of the middle of this journey. There is no tracking data. There is no observation log covering the 31 years it spent going around the Sun, because for 31 years, as far as anyone on this planet was concerned, it did not exist. What we have is a beginning we recorded and an ending we stumbled into by accident. Everything between those 2 points is reconstruction. It is physics, run backwards. A computer taking a handful of measurements from a few nights in 2002 and calculating what path must have delivered the object to that exact spot, then extending that calculation back across 3 decades in which no one confirmed anything, which reframes the entire investigation. This is not really a story about a piece of a rocket. It is a story about how much of a 30-year journey you can recover from a few grams of reflected sunlight, and about the exact point at which that reconstruction stops being reliable, because the work that followed had to answer 3 separate questions, in order. The first was what the object was made of, which would establish whether it was ours at all. The second was where it had been, which meant running the clock backwards to find out how long it had been away and when it had left. And the third was whether those 2 ends could be connected, whether the object photographed in 2002 could be traced continuously back to a specific vehicle, on a specific launch pad, on a specific day in 1969. 2 of those questions got clean answers. The third one did not. And it still has not. There were 2 competing explanations on the table, and they could not both be right. The first was natural. J002E3 was a rock, a piece of asteroid roughly 30 meters across, that had wandered close to the Earth and been temporarily grabbed by our gravity. Rare, but not impossible. The second was artificial. J002E3 was something we built. The difference between those 2 answers is enormous, and there was one measurement that could settle it. Not where the object was, not how fast it was moving. What it was made of. Here is the principle. When sunlight lands on a surface, some wavelengths bounce off and some get absorbed. Which wavelengths get absorbed depends on the chemistry of that surface. A rock rich in iron absorbs a different set of colors than a rock rich in silicon. Aluminum absorbs a different set again, and so does paint. Spread that reflected light out into a spectrum, and the absorption gaps act like a fingerprint. You do not need to touch an object to know what its skin is made of. You only need enough light. The problem was that J002E3 was faint, and one telescope working alone could only cover part of the spectrum. So 2 teams ended up working the same target from opposite ends of the light range without initially knowing about each other. At MIT, Professor Richard Binzel and research scientist Andrew Rivkin were observing the object in infrared using NASA's Infrared Telescope facility. In Arizona, Carl Hergenrother and Rob Whiteley at the Lunar and Planetary Laboratory were observing it in visible light from Steward Observatory in the Santa Catalina Mountains. Neither dataset was conclusive on its own. Rivkin was still puzzling over the first night's numbers when an email arrived from the Arizona team. They combined the 2 sets, and the combined spectrum, stretching from visible light into the near-infrared, produced a shape that neither team had gone looking for. The object was covered in paint. Sit with that for a moment. Not a mineral signature, not a metallic asteroid. The absorption features matched a mixture of white paint, black paint, and aluminum, and the strongest single match, in the near-infrared, was to a paint containing a titanium oxide semiconductor. Titanium oxide is the compound that makes white paint white. It is also extremely good at reflecting heat, which is why it was used on rocket stages that had to sit in direct sunlight without cooking their own fuel. And there was one family of vehicles painted with exactly that compound that had once been sent out past the moon and never brought home, the Saturn V. So the identification of the material did not solve the mystery. It rewrote it. The question was no longer whether J002E3 was an asteroid. The question was, which piece of the Apollo program was floating around out there 33 years after we lost track of it? Chemistry told us what the object was. To find out where it had been, the work moved to a different discipline entirely. At NASA's Jet Propulsion Laboratory, Paul Chodas and Steve Chesley began doing something that sounds simple and is not. They took the object's measured positions and ran the physics in reverse, asking the computer to reconstruct the path that would have delivered it to that exact point in space at that exact moment. Orbital mechanics is, in principle, deterministic. Give a computer the position and velocity of an object and the gravity fields acting on it, and it can march the calculation forward or backward in time as far as you like. In practice, it is a fight. The trouble starts with what you actually have to work with. A telescope does not measure an object's position in 3 dimensions. It measures a direction, a point on the sky, and nothing about distance. Everything else has to be inferred from how that point drifts over hours and nights, and from how the geometry between the observer, the object, and the sun changes as it moves. Which means that early orbit solutions are not answers. They are a family of possible answers, and the family narrows every time somebody else points a telescope at the same spot and reports another position. That is why the amateur observers matter here, and not as a courtesy. The professional facilities were not sitting idle, waiting for faint, unidentified dots. Much of the tracking that turned a rough solution into a precise one came from people running modest telescopes in their own time, submitting measurements to a central clearinghouse and letting the numbers accumulate. The first problem showed up almost immediately. In late September, J002E3 crossed into the daytime sky and was briefly unobservable. About a week later, amateur astronomers Richard Frederick and Vance Morgan recovered it from Powell Observatory in Kansas after it had moved into the evening sky. But their measurements did not land where the predictions said they should. The object was slightly off, not dramatically, just enough to say that the model was missing a force. That missing force turned out to be sunlight. Light carries momentum. When photons strike a surface, they push. On Earth, this is far too small to notice against wind and friction. In space, over months and years, acting on something light for its size, that pressure becomes a real acceleration. It has to be in the model, or the model drifts. And here is the important part. Solar radiation pressure depends on how much surface area is facing the sun, which depends on how the object is oriented, which depends on how it is tumbling. For a solid sphere, that does not matter much. For a hollow cylinder that is turning end over end, it matters a great deal. The push is not constant. It changes with the object's rotation and with its distance from the sun. And to account for it precisely, you need to know the axis the object is spinning around. Nobody knew that axis. So the reconstruction was built with an unavoidable margin of error baked into it, and that margin grows the further back in time you push. This is worth holding on to, because it is going to matter later. An orbit like this does not keep a clean record of its own past. The further back you run the clock, the more the possible histories spread apart. Even so, the reconstruction produced a clear result. J002E3 had spent roughly 31 years going around the Sun, and before that, it had been in the neighborhood of the Earth in 1971. 1971 is a very specific year to land on. It narrows the list enormously. The obvious candidate was Apollo 14, which flew to the Moon in early 1971. And for a short while, that looked like the answer. It was not. NASA knew where every major piece of Apollo 14 hardware had ended up, and the upper stage in particular was not a mystery. It had been deliberately steered into the Moon and crashed there on purpose to make an impact large enough to register on seismometers already sitting on the lunar surface. Its location was not just known, it had been chosen. So the search moved along. And to understand what it moved along to, you need to know what the object we are looking for actually is. The Saturn V was a 3-stage rocket. The first 2 stages did the brutal work of getting off the ground and out of the thick atmosphere, and both fell away within minutes. The 3rd stage was different. It was called the S-IVB, just under 18 meters long, about 60 feet, and roughly 3 meters across. It carried a single engine that could be shut down and restarted, which was the entire point of it. The S-IVB fired once to help push the spacecraft into a parking orbit around the Earth. Then it shut down, and everything coasted while the crew and the controllers checked that the vehicle was healthy. Then, on command, it lit a second time for a burn of several minutes. That second burn was called translunar injection. It was the moment a mission stopped orbiting the Earth and started falling toward the Moon. After that, the S-IVB had no further job. The crew's spacecraft pulled away, turned around, docked with the lunar module, and extracted it from the top of the spent stage. And then 14 metric tons of empty rocket had to be disposed of. NASA used 2 different disposal methods across the program, and the split is what makes this story possible. The later landing missions, Apollo 13 through 17, aimed their third stages at the Moon on purpose for the same seismic reason as Apollo 14. Deliberate impacts, known coordinates. But the middle missions were handled differently. Apollo 8 through Apollo 12 all sent their third stages out of the Earth-Moon system entirely, into orbit around the Sun, where they would never come back. And there is a detail buried in that split that is easy to walk past. The reason the later stages could be crashed into the Moon usefully is that there were instruments on the surface to hear them. Deliberately impacting a 14-ton object is only worth doing if something is listening. The first of those listening devices was the seismometer that Conrad and Bean had left behind in the ocean of storms. On Apollo 13, the third stage was aimed at the Moon and hit it, and the tremor was recorded by the instruments Apollo 12 had deployed. The impact site was located about 135 kilometers west of where Conrad and Bean had walked. So, Apollo 12 is the mission that made the new disposal method possible. It is also the last mission that used the old one. That was the plan anyway. And when investigators worked through which of those 5 stages could still be unaccounted for and matched that against the orbital reconstruction and the paint, the answer that survived was Apollo 12. November 14th, 1969, Kennedy Space Center. The weather is bad. There is heavy cloud over the pad and rain in the area. The conditions are inside the launch rules as they were written at the time. And the rules at the time did not say very much about electricity in clouds. Apollo 12 lifts off at 22 minutes past 11 in the morning, local time. On board are Charles Pete Conrad, Richard Gordon, and Alan Bean. 36.5 seconds later, at an altitude of around 6,000 feet, lightning strikes the vehicle. It does not strike out of nowhere. The rocket's exhaust plume is a long column of hot ionized gas running from the engines all the way back down to the ground, and that column conducts electricity. The Saturn V, climbing through a charged weather system, has effectively built a wire between the clouds and the launch pad. The discharge runs straight down it. 16 seconds after that, at 52 seconds into flight, it happens again. Inside the command module, the warning panel lights up. 3 fuel cells drop offline. The guidance platform loses its orientation. Conrad reports what he is seeing, and what he is seeing is essentially every alarm the spacecraft has. But in mission control, the situation is worse, and in a stranger way. The telemetry, the continuous stream of numbers that tells the ground what every system on the vehicle is doing, has turned into nonsense. Not zeros, not blank screens, garbage. Readings that do not correspond to any failure anyone has ever seen because they do not correspond to reality. There is a rocket accelerating through the atmosphere with 3 people on it, and the room responsible for it has just gone blind. At the electrical and environmental console sits a flight controller named John Aaron. He is in his 20s. He is not senior, and he is looking at the same meaningless numbers as everybody else, except he has seen them before. About a year earlier, during a ground test, Aaron had watched telemetry go strange in exactly this pattern. Most people in the room that day treated it as noise and moved on. Aaron did not. He followed it back to a component called the signal conditioning equipment, the box that converts raw sensor readings into the signals the ground receives, and worked out that when the power supply to that box sagged below a certain level, it produced this specific flavor of gibberish. He also learned that the box had a backup mode that would keep it working at low voltage. Nobody had any particular reason to remember this. It was, by any reasonable standard, a useless piece of knowledge. Aaron's call is 5 words long. Try SCE to auxiliary. The flight director does not recognize the switch. Neither does the capsule communicator, who has to ask where it is. Conrad, hearing it relayed, repeats it back wrong. Alan Bean knows. The selector is on the lower right of the main console, near his position. He reaches over and moves it. The telemetry comes back. It does not fix the spacecraft. The fuel cells still have to be brought back online, the guidance platform still has to be realigned, and the crew and the ground still have to go through the vehicle system by system to confirm nothing is permanently damaged. But it gives mission control its eyes back, at the one moment in the flight when being blind is fatal. Apollo 12 reaches orbit. The crew and the ground spend the next hour and a half going through the electrical system with unusual care. Nothing is broken. On the second lap around the planet, Houston gives the signal, and the third stage lights for the second time, a burn of 5 minutes and 41 seconds, and sends the mission to the moon. Now, the reason Apollo 12 exists at all is worth understanding, because it explains why this mission was carrying a very particular kind of pressure. 4 months earlier, Apollo 11 had landed. But it had not landed where it meant to. Neil Armstrong had taken semi-manual control to steer clear of a boulder field, and Eagle touched down more than 6 kilometers from its intended target. That was fine for a first attempt. It was not fine as a plan. Because if you cannot control where you land to within a few hundred meters, then you cannot send crews to specific geological features. You can only send them somewhere flat and hope it is interesting. The entire scientific future of the program depended on solving that problem. So Apollo 12 was given a target that would prove it either way, not a region, an object. Surveyor 3 was a robotic lander that had set down in the ocean of storms in April 1967 and then sat there, silent, for 2.5 years. A lunar scientist named Ewan Whitaker had worked out its precise position from orbital imagery. If a crew could land close enough to walk over to it, the pinpoint landing question would be answered permanently. During the descent, Conrad was expecting to see a specific arrangement of craters. The crews had nicknamed the Snowman a pattern with individual craters they had labeled head, left foot, right foot. He had privately feared that when the lunar module pitched over and gave him his first look at the ground, he would see nothing he recognized. He saw the Snowman, exactly where it was supposed to be. Conrad set Intrepid down northwest of Surveyor Crater on November 19, 1969. The distance to Surveyor 3, measured afterward, was about 538 feet. Conrad and Bean stayed on the surface for a little over 31 hours and made 2 moonwalks totaling somewhere close to 8 hours. They collected around 34 kilograms of rock and soil. They walked down to Surveyor 3, photographed it, and cut off pieces of it, including its television camera, to bring home so that engineers could examine what 2.5 years of lunar exposure does to hardware. They also deployed a set of instruments called ALSEP, powered by a nuclear generator, and left it running. One of those instruments was a seismometer. Richard Gordon spent all of it alone in lunar orbit, running his own observation program from the command module. The mission was, by every measure that mattered at the time, a complete success. And in all of that, almost nobody notices what happens to the third stage. Getting rid of an S-IVB was not as simple as letting go of it. The stage was empty, but it was not entirely inert. There was leftover propellant in the tanks, and that residual propellant was the tool used to steer the thing away. The sequence went like this. First, the crew's spacecraft separated and moved clear, and the S-IVB performed a small, evasive maneuver so the two vehicles would not stay near each other. Then, on ground command, the stage vented its remaining propellant. Venting is not a rocket burn in the conventional sense, but it works the same way. Gas leaving a tank in one direction pushes the tank in the other. Do it in a controlled way, at the right moment, and you can nudge a 14-ton object onto a new path. The path they wanted was a flyby of the moon. Now, this is the part that is worth slowing down for, because it is not intuitive. If you fly a spacecraft past a large body, you can steal energy from it. The moon is moving. Its gravity grabs the passing object, swings it around, and lets it go pointing in a different direction and traveling faster relative to the sun. The moon loses an unmeasurably small amount of orbital energy. The spacecraft gains enough to change its fate. That is a gravity assist. And for Apollo 12's third stage, a properly executed one would have added just enough speed to push it past escape velocity out of the Earth-Moon system and into a permanent orbit around the Sun. Gone for good. The maneuver depended entirely on how close the stage passed to the Moon. Closer means a stronger swing and a bigger boost. Too far means not enough. And on Apollo 12, the ullage engines, the small thrusters used to settle the propellant before venting, burned for longer than intended. That is the whole thing. That is the mistake. A small motor ran too long, which changed the amount of velocity imparted, which changed the trajectory, which meant the stage passed the moon at a higher altitude than planned on November 18th, 1969. The slingshot still happened. It just was not strong enough. The S-IVB came away from the moon with more energy than it went in with, but less than it needed. Not enough to escape. It settled instead into an enormous, stretched-out orbit around the Earth, coming into roughly 100,000 miles at its nearest point and swinging out past 500,000 miles at its farthest, taking about 42 days to complete one lap. For comparison, the Moon orbits at an average of about 240,000 miles. So this thing was crossing the Moon's orbit twice on every pass. That is not a stable arrangement. It is a coin standing on its edge. For roughly 2 years, the stage looped around the Earth in that unstable orbit, getting pulled a little differently on every pass depending on where the Moon happened to be. And in 1971, one of those passes finally gave it the push it had been denied in 1969. It escaped. It went into orbit around the Sun, and with no beacon, no transmitter, and no reason for anyone to look for it, it stopped being an object and became a footnote. That is the moment the clock starts. Sometime in 1971, a 14-ton cylinder crossed out of the Earth's influence, and nobody on this planet recorded it happening or noticed that it had. The next confirmed observation of it is 31 years later, on a photographic plate in an amateur's back garden. So how does a piece of hardware in orbit around the Sun end up in orbit around the Earth again 3 decades later without firing an engine? The answer requires letting go of a simplification most of us learned early. We are usually taught that orbits are the result of one big object pulling on one small object. 2 bodies, 1 ellipse, clean math. That model is excellent, and it works right up until a third body gets involved. Add a third gravitational source, and the problem stops having a neat solution. There is no equation you can write down that predicts the path forever. You can only simulate it, step by step, and the answer you get depends sensitively on where you started. An object drifting near the Earth is not in a 2-body situation. It is being pulled by the Sun, by the Earth, and by the Moon, and the relative strength of those pulls changes constantly as everything moves. Inside that mess, there are special locations where the pulls come close to balancing. They are gateways more than places, regions where an object needs almost no energy to change its allegiance from one body to another. Drift through one going slowly enough, and you can be handed off from an orbit around the Sun to an orbit around the Earth without anything dramatic happening at all. That is what the modeling says happened in 2002. After 31 years going around the Sun on a path that stayed close to the Earth's own, the object came back around and approached from the right direction at the right speed, and Earth's gravity took hold of it again, not by catching it, by quietly outvoting the Sun. The orbit it fell into was chaotic in the technical sense. Every loop was different from the last. It passed close enough to the Moon's orbit that lunar gravity was reshaping the path continuously. When Chodas and Chesley ran the numbers forward, the early forecasts could not even rule out an impact with the Earth or the Moon within the following year. With more observations, that uncertainty collapsed. It became certain that the object would leave the Earth-Moon system in June of 2003, and that no collision was possible for decades. It made about 6 loops around the Earth in total. And then, in June 2003, it went out through the same kind of gateway it had come in through, and returned to orbit around the Sun. The whole visit lasted a little over a year, which is worth sitting with. 31 years away, 12 months back. And in that narrow window, everything we will ever know about this object had to be measured, because when it closed for another 4 decades. Before it left, there was one more measurement worth taking. In February 2003, observers at the Air Force Maui Optical and Supercomputing Site tracked the object and recorded not its position, but its brightness, moment by moment. This technique is called photometry, and it is one of the most useful tricks in the field. A tumbling object does not shine steadily. As it turns, the amount of surface facing you changes, and the brightness rises and falls. Record that rhythm carefully, and you can work backwards to the object's shape and rotation. The pattern that came back was regular. The object was completing a rotation every 63.5 seconds and not spinning cleanly around a single axis. The measurements indicated a near end-over-end tumble, the motion of an object turning like a thrown baton rather than a spun top. The reconstructed shape was a cylinder. The reconstructed size fit an S-IVB. And there was a detail inside those numbers that is easy to miss, and, in some ways, is the quietest evidence in the whole case. When the team worked out how reflective the surface must be to produce the observed brightness, the answer came back lower than fresh white paint. The surface was darker than it should have been. That darkening is what space does to paint. Out there, with no atmosphere in the way, a surface takes the full, unfiltered ultraviolet output of the Sun, plus a steady sandblasting of charged particles from the solar wind, plus the swing between direct sunlight and deep shadow. Over decades, that breaks down the binders in the coating and dulls it. The white goes gray. So the light curve was not only saying, this is a cylinder about 18 meters long, it was saying, this is a cylinder about 18 meters long that has been out there a very long time. To understand how unusual this object is, it helps to know what the alternatives look like. 10 essentially identical S-IVB stages flown on Apollo, Skylab, and the Apollo-Soyuz mission came back down into the Earth's atmosphere between 1966 and 1975. Every one of them burned up and broke apart on the way in. None arrived as a single piece. The largest example was not a spare stage at all. Skylab, America's first space station, was built inside a converted S-IVB hull. It weighed around 77 metric tons, more than 5 times the mass of the empty Apollo 12 stage, and when it came down in July 1979, it also broke up. But those objects were all falling from low orbit, or from a path that never left the neighborhood. Something arriving from solar orbit carries more energy. Then there is the other category of confusion, and it runs in both directions. In 2006, an object designated 2006 RH-120 was found in orbit around the Earth and assumed to be space debris. It turned out to be a genuine natural object, a small asteroid that Earth had temporarily captured. A real, if brief, second moon. The reverse has also happened. In 2007, an object was given a formal asteroid designation before anyone realized they had catalogued the Rosetta spacecraft. In 2020, an object called 2020 SO was tracked as a near-Earth asteroid and later identified as a discarded rocket booster from the 1960s. And there is a stranger category still. Since 1956, when the Polish astronomer Kazimierz Kordylewski first reported them, astronomers have discussed the possible existence of faint, transient concentrations of dust suspended at gravitationally balanced points in the Earth-Moon system. Not solid, not permanent, just dust that has found somewhere temporarily comfortable to sit. Now, take a step back and look at what that list actually contains. A rock we mistook for debris. Debris we mistook for a rock. An operating spacecraft that was formally catalogued as an asteroid. A rocket booster from the 1960s that spent months in the near-Earth object databases before anyone worked out what it was. And clouds of dust that may or may not be there at all. The pattern is consistent, and it is not a failure of competence. It is a limit built into the method. When an object is faint and far away, the only information reaching us is a small amount of reflected sunlight. From that light, we can extract a direction, a brightness, and if we are patient and the object cooperates, a spectrum and a rotation. That is a lot. It is also not the same as knowing what something is. Everything beyond that comes from inference. And inference works by comparing what you see against what you already know is possible, which is exactly why J002E3 was hard. For the first several days, nobody was comparing it against the right catalogue. So here is what the comparisons actually tell us. The space around our planet is not empty, and it is not clean. And it is no longer possible to assume that a new object out there is natural. We have been launching hardware for long enough that some of it has now been gone longer than most of the people looking for it have been alive. We are, in a small but permanent way, now part of the background. There is one more thing about this case that deserves to be stated plainly, because it tends to get smoothed over. We never proved it. The identification of J002E3 as the Apollo 12 third stage is the best available explanation. It is supported by the spectrum, by the shape, by the rotation, by the size, by the surface weathering, and by the process of elimination across the disposal records of the entire Apollo program. It is a strong case. Researchers have described it as most likely, and that phrasing has been consistent since 2002, but strong is not the same as closed. The step that was never completed is the one that would have made it airtight, connecting the motion of the object observed in 2002 continuously back to the last known position of the Apollo 12 stage in 12 videos, 1969. The team at JPL said so directly at the time. They were unable to make that connection. There were two reasons, and both of them come back to things we have already talked about. The first is sunlight. Solar radiation pressure varies with the object's distance from the sun and with which face is turned toward it. To model that precisely across 33 years, you need to know the object's rotation axis. That was never determined. The second is deeper, and it is the one that was quietly seeded earlier in this story. If J002E3 is the Apollo 12 stage, then it spent more than a year in a highly chaotic orbit around the Earth before escaping in 1971. Chaos, in this context, has a precise meaning. It means that two nearly identical starting conditions will produce wildly different outcomes given enough time. Run the simulation backwards through that period, and the tiny uncertainty in your present-day measurement does not stay tiny. It expands. What was a small error becomes a fan of possible histories, spreading wider with every year you retreat. The object went through a region of its own past that erases the trail behind it. So what does that mean, in practical terms? It means we have an object whose material is human-made, whose shape and size match a specific vehicle, whose rotation matches that vehicle's expected behavior, and whose surface shows the wear of decades, and we cannot walk the path backwards to say with certainty that it is the one we think it is. We know what it is. We are very nearly certain whose it is, and the mathematics that connects those two statements does not survive the journey. Since June 2003, the object has been in orbit around the Sun. It is not being tracked in any continuous way. There is no transmitter on it, and nothing to listen for. It is a dark, dulled, tumbling cylinder somewhere along a path that stays broadly near the Earth's own orbit, too faint to see, except under specific circumstances. The models say the earliest opportunity for the Earth to capture it again is in the mid-2040s. That is not a prediction that it will happen. It is a statement about when the geometry could next permit it. And the uncertainty on that forecast is large, for exactly the reasons already covered. Long-term integrations have to account for the gravity of the planets and for the accumulated push of sunlight. And near the balance points of the Earth-Moon system, the paths are chaotic. By the 2040s, the region of space where the object could plausibly be is not a point, it is a smear. Its longer-term future is genuinely open. Its orbital paths around the Earth carried it inside the Moon's orbit, which means that on some future visit, entry into the Earth's atmosphere or a collision with the Moon are both possible outcomes. Neither is predicted. Both are permitted by the physics. If it did come down, it would be a 14-ton object entering with more energy than the stages that came home in the 1960s and 1970s. Objects of roughly that mass do reach our atmosphere something like 10 times a year. Almost all of them break up completely, but it is worth being honest about the timescale of our attention here. The people who built this stage designed it to work for a few hours. It performed its 2 burns, released its spacecraft, vented its tanks, and was written off as expended before the crew it launched had even reached the Moon. Its working life was measured in hours. Its actual life is now measured in decades, and there is no end date on it. There is something worth noticing about how this story is put together. Every element of it came from a small margin. A launch that went ahead in weather the rules did not yet know how to judge. A telemetry pattern one person happened to study when nobody asked him to. A switch almost nobody in the room could name. A motor that ran a few seconds longer than intended. None of those were dramatic at the time. The lightning strikes were resolved before the vehicle left the atmosphere. The long ullage burn was not even a failure by the mission's own standards, because the mission was about landing 2 people next to a robot in the ocean of storms, and it did that. The 3rd stage was garbage. Its disposal was a footnote in a report. And the footnote is the part that is still out there. That is the pattern that keeps repeating in spaceflight. The things we plan for carefully tend to end on schedule. The things we do not think about tend to keep going. We built an object to be discarded it slightly wrong, and by doing so, accidentally placed it into one of the most delicate, dynamical situations in the solar system, a place where the Sun and the Earth and the Moon pull with nearly equal authority, and nothing keeps its identity for long. It orbited the Earth, then it orbited the Sun, then it came back and orbited the Earth again for a year, while an amateur astronomer, 2 university teams, and a group of orbital dynamicists worked out what it was, and then it left again before we could finish the sentence. We have a spectrum. We have a light curve. We have a rotation period measured to a fraction of a second, and a shape, and a size, and a surface that has been weathered by 33 years of unfiltered sunlight. We have almost everything. What we do not have is the one thing that would let us say the word certainly. Somewhere out there, on a path we can only approximate, a 14-ton cylinder of aluminum and faded white paint is turning end over end in the dark. It was built by people who are mostly gone now, for a journey that was supposed to last 3 days. It has been traveling for more than half a century. It does not know where it came from. Neither, entirely, do we.